In the previous clip, I showed how a simple model could win against a more complex one. While a more complex model is more adaptable and can fit the incoming data better, it will not necessarily predict the data better. Having extra complexity could help a model adapt, and this adaptation can help predict incoming data, but only up to a certain point, beyond which introducing more complexity will only harm the prediction power. Adding extra parameters to fill with can simply introduce more uncertainty into the model. And that indicates that there is a Goldilocks zone, a complexity level that is just right for the job. Go more simple than that and you will not catch salient features and predict worse than a model with these features. Go more complex than that and the extra parameters will only cloud your vision and make your predictions worse. And prediction power tells us what constitutes evidence and determines in which direction the model probabilities are going. Something like this principle has been proposed long ago by a friar named William of Occam. Quoted more or less directly, he said that entities should not be multiplied beyond necessity. In more everyday language, all things being equal, the simplest solution is the best. Stated in model language, choose the simplest model that describes the data sufficiently. This is actually a guiding principle in both frequentist and Bayesian statistics. However, in Bayesian statistics, probabilistic reasoning if you will, this is something that comes natural, and I'll give an example of this. So, let me introduce the example. Here's a nice physical device in the form of Lego. There's a chute leading down to a seesaw. Drop a steel ball down the chute and it will bounce through and hopefully hit the seesaw, thus launching a Lego brick into a trajectory that is meant to end inside a designated area. If that happens, the trial is called a success. On the top of the chute I've installed another seesaw where I place the steel ball. When I remove my finger from the seesaw, it should release the steel ball, and this should ensure a certain control of the initial state of the system. The object is to throw everything we've learned so far at this setup, from very simple models to very complex ones. Since there are only two outcomes contemplated here, success or failure, we can stick more or less to the models we've already encountered. Now I have a certain control of the initial state of the system, and since this system can be fully expected to follow Newton's laws, which are deterministic, saying that either all trials will end in success or in failures must seem very plausible. So my first model, which I've called N0 for Newton 0, is that the success rate P is 0, and that means that failure is assured. There are no free parameters in this case, the model is locked. This immediately suggests the countermodel, namely N1 P equal to 1, meaning that success is assured. Now I've been careful about the initial conditions, but the chute is laced with small studs, making the ride down like a flipper game. So any small uncertainty in the initial conditions may translate into anything at the other end. So you can also contemplate models where the outcome is stochastic, meaning that they have a degree of uncertainty associated to them. And the simplest way to do that, S2, is simply to assume independence between trials and symmetry between failure and success, and give each a 50% probability. Of course, with this setup in mind, it could be hard to justify such a symmetry. Without any special justification for the success probability, we can start to look at a model where it can be anything. So let's skip ahead to the next model where each trial is independent from the next and where the success rate P is a free parameter. I've called this FP for free P, though I've earlier called it the free binomial model. Basically, I initially say that each value of P is equally probable. So initially I have symmetry between success and failure, though that will change when the model adapts to the data. Next up, MC is the simplest time-dependent model, a Markov chain, where each outcome probability of one trial depends on what happened in the previous trial. So that's a model with two free parameters. Then we can start contemplating a model where what we've learned so far only helps us up to a certain point in time. In this case, I'm contemplating that each batch of 50 measurements are independent sources, meaning that what you learn from trial 1 to 50 can't be used for predicting beyond that. On trial 51 you're back to scratch again and have to start learning all over again. Here the number of parameters will grow with the number of data as n divided by 50 rounded upwards, where n is the number of measurements. Not a nice model, but as long as you don't want to predict too far, you can. I've called this FP50 for free P50, though the F could also stand for forgetful. Similarly, we can contemplate a model where we go back to scratch each 10th trial, a very forgetful model. So the number of parameters here will be n divided by 10 rounded upwards. I'm using these two models as a stand-in for a greater model family where the time until you have to reset is unknown, i.e. free. If I wanted to explore such a model, I would need a prior distribution for the reset time. Now for the reset times larger than the number of measurements, these submodels will behave exactly like the free success rate FP. Now I don't want to spoil the excitement, but if, and I only say if, we get evidence for the simpler FP model against the submodels with repeat time less than the number of measurements, then the whole model will take a dive. The principle behind this is explained in clip 5, the shrinking model family. Still, I don't want to go to that detail level, so I'll only use model FP50 and FP10 as stand-ins for this larger model. Next up, let's go to the logical conclusion of all these models. Let's assume that every trial is something unique that says nothing about the next trial. There's no need to put a probability on each trial directly here. Each trial is now seen as preordained by an inscrutable fate. Now with unscrutable I do not mean not entirely scrutable. I mean absolutely not scrutable at all. A submodel of this is that everything that happens by the will of an omnipotent, inscrutable God. I don't think many believe in this particular concept of God. There may be some, but if you think you are one of them, then maybe if you dig a little deeper, you'll find that you don't believe in what you believe you believe. The model, which I've called IF1, Inscrutable Fate 1, can adapt perfectly to all incoming data. Now, I've simply extrapolated the reset models I've been working on and put a complete ignorance prior on whether the preordained outcome will be a success or a failure, meaning that it will not predict any differently from the symmetric 50-50 model S2. This may seem a little silly. It could work in the case of the brick landing here, but what if we instead looked at success as the brick landing here, or here, or here? These instances can't all have probability 50%. If we want to take the idea of inscrutability seriously and try to make a consistent model of everything, then the only option I see is if any particular kind of outcome disappears into an infinite sea of entirely unfathomable outcomes. So the last model will be that we put a prior on each preordained outcome to 0 for success and 1 for failure. This will be called IF0, and while it too will be able to fit the data perfectly, it will predict exactly the same as Newton 0.